to quiz 2 for Math 252. I have this big bold note here talking about how hard this quiz is. Maybe that was a bad idea. I hope that didn't freak anybody out when you started this thing. The first question asks you to essentially estimate the area under this curve from here to here. And it wants you to estimate it by calculating R4. So to figure out the height of the rectangles that you will be using, you'll use the right endpoint. So you can do this a couple of ways, or you can kind of denote this a couple different ways. R4 is the sum from I, it's supposed to be an I, equals 1 up to 4 of our function x squared, but it's actually xi that's being squared because this thing is going to change in each copy of this sum, times the length. Maybe I should put f of xi. Let's do that in the next step. I'll change it to xi squared. F of xi times delta x. Each rectangle has a height and a width, and we're going to add up the 4 different rectangles. So we got to figure out what to put in here. Well, delta x is always b minus a over n. Essentially, it's saying the entire length you'll want to span is from 4 to 2, so a width of 2 here. But you're going to have 4 rectangles, so you got to divide by 4 to figure out the width of each rectangle. You got 4 minus 2 divided by 4, aka 1/2. So delta x equals 1/2. Xi, you can either just kind of reason your way through this, or you can denote it algebraically like I'm doing here. But xi is going to be a plus delta x times I. So a is still 2, and delta x is 1/2, and 1/2 times I is I over 2. So essentially what I'm saying here is x1 is 2.5, because I would be equal to 1. x2 is 2 and 2/2, aka 3. So on. So you can either denote your x's that way or keep them like this. So what you're trying to figure out is the sum from I equals 1 up to 4 of f of xi, okay, times delta x. So actually, I'm not even going to write this in summation notation. What I'm going to do is say every single term in this summation is going to have a delta x in it, so I can factor that out in front to get this 1/2. And then what I'll just figure out is what is each of the f of xi's. Well, f of x is x squared. So what I have to do is figure out x1 squared. Well, x1 is 2.5, aka 5/2. So x1 squared would be 5/2 squared. And x2 would be 2 and 2/2, aka 3. So x2 squared would be 3 squared. And so on, we get 7/2 squared plus 4 squared. And now if I just do some calculations here, let's see, 5/2 squared is 25/4. 3 squared is 9. 7/2 squared is 49/4. And 4 squared is 16. So I get my answer is 1/2 times, let's see, 25 and 49 is 74/4. And 9 and 16 is 25. But 25 is 100/4. So 174/4. But I can simplify times 1/2. Let's see, half of 174 is what, 87? So I think I end up with 87/4 as my answer here. I guess that's all. You can write your answers up a little bit differently in terms of the steps you show, but as long as you come up with your answer, I'm a happy man. Alright, now I want you to not do these calculations again, but just show that you understand M4. So M4 is the same basic idea. I'm going from 2 to 4. So here's 2 right here, and here's 4. And I want to make 4 rectangles. So the width of the rectangles is 1/2. There's kind of the 4 rectangles right here. But figuring out the height of the rectangle is a little bit tricky. Instead of using the right endpoint to figure out the height of the rectangle, I'm going to use the midpoint. So the midpoint right here will help me determine the height of the rectangle. And it's hard to draw on my computer, but what I'm getting at is you'll get a rectangle that looks something like that, because this point right here is on the curve, and it's the midpoint of this interval. And then do the same thing. Here's the midpoint here, and it looks like that intersects the curve right around there. So now you'll want to draw rectangles that go through that point, which is a little bit hard to do, but we'll call that good enough. And same thing, it's almost a straight line, and it intersects, I don't know, right around there. And if you didn't want to trust your drawing, you could calculate all these intersection points on your own. But you don't have to. I just needed a picture of this stuff. Hopefully I can make that clear in class. And so finally, my last rectangle should have this height. There it is. So if I figured out the area of these rectangles right here, added them all up, whoops. Yeah, that's just getting worse. There you go. Add up the area of these 4 rectangles, you get M4. That's it. That's done with part B. Part C, rank these from least to greatest. Okay, so what you need to know is that because, I should write this, because my function is increasing, using the left endpoint, I mean, you can kind of just see it here. If I use the left endpoint, my rectangle would be this guy. If I use the right endpoint, my rectangle would be this guy. The left endpoints, my rectangles would all be less than the true area. The right endpoints, my rectangles would all be more than the true area. What I'm saying is that because the function is increasing, L sub n will be an underestimate. And similarly, R sub n will be an overestimate. So what that tells you is that, I don't know, L4 is smaller than R4. Nope. Yeah. And L40 is smaller than M40. But what about the rest of them? What about L4 versus L40? As n increases, accuracy increases. So what I'm saying is L4 is not only an underestimate, it's a big underestimate because this is not nearly as accurate as L40. So this is a far bigger underestimate than this guy is. So my smallest is going to, maybe I should write so here. So if I'm ranking these guys, L4 is actually the smallest. My next smallest will be L40. My next smallest will be R40. And then my largest will be R4. And it's sort of like the true answer is somewhere right in here. This one's a little bit smaller than the true answer. This is a little bit bigger than the true answer. This is way smaller than the true answer. This is way bigger than the true answer. You get something like that. I don't know, a little bit theoretical here. I don't know if this was a good question or not. Moving on. All right, this thing. I almost feel bad asking you to do this, but I don't know. Here we are. So what I want you to do is determine the area under the curve. So it's kind of like you're doing this again, except now you're not estimating it. Now you're not finding R4, you're finding the exact area under the curve. What you're finding is the integral from 2 to 4 of your function x squared dx. And you're like, oh, no problem, that's super easy. Yeah, except it's not in 5.2. Because in 5.2, we don't have the evaluation theorem, the fundamental theorem of calculus part 2, that says that, yeah, you can figure this out just by using antiderivatives. Bummer. So we had to do it the long way, which told us that by definition, this thing is equal to the limit, as n approaches infinity, of the sum from I equals 1 to n of f of xi, and really it could be xi star if you care, I don't know if you care, times delta x. And how the hell am I going to figure this out? Well, delta x, like I figured out before, is still b minus a over n. Sure, I'll write it. And b is still 4, and a is still 2. Problem is now n is just n, so delta x is 2 over n. And xi is a plus delta x times I. The way to think about it is xi is telling you which point down here we're talking about. Well, we're starting at 2, and then x1, I'll just be adding 1 delta x. x2, I'll be adding 2 delta x's. x3, I'll be adding 3 delta x's. So I get I of these delta x's each time I increases. So I know that a is equal to 2, and I know that delta x is 2 over n. So I get something like this for xi. So what that I can then do is come back up here and say this is the limit. I'm not going to want to write this over and over again. I'll do it this one last time. Of the sum from I equals 1 to n of, and then instead of f of xi, well, xi is this thing. So I got 2 plus 2i over n. But you don't just want xi, you want f of xi. Oh, right, f of x is the squaring part of it. And you want to multiply that by delta x, which is 2 over n. Okay, so now you have a sum. You want to rewrite this sum so that it's just the sum of the number 1, the sum of I, or the sum of I squared, because those are the 3 hints that I gave you here. So I got the limit as n approaches infinity of, let's mess with this sum. I got the sum from I know I said I wouldn't write this again, I equals 1 to n of, if you expand this thing, you would get 4 plus, and then the O and the I in FOIL will be the same. Both of them will be 4i over n. So if you add 4i over n and 4i over n, you get 8i over n. And then the L in FOIL would be 4i squared over n squared. But you got to multiply all of those by 2 over n. And this might be too many steps to do it once, but I don't want to keep writing this thing. Cut me some slack. It's been the end of a long day. 2 squared is 4 times 2 over n is 8 over n. Plus 2 times 2i is 4i divided by n, but I have 2 of them, so I have 8i over n. But I have to multiply that by 2 over n, so I have 16i over n squared. And then 2i over n times 2i over n is 4i squared over n squared, but when I multiply that by this 2, I get 8i squared over n cubed. So I get to here. Okay, so this is the limit as n approaches infinity of this mess of a sum. Unfortunately, I don't know how to evaluate this sum right here. What's the sum from I equals 1 to n of this weird polynomial? No clue. However, when I have a sum, it's just a whole bunch of copies of this. So I'm just adding this plus this plus this plus this. Because addition's commutative, I can change the order that I'm adding those things in. So I can think about it like there's an 8 over n in the first copy, there's an 8 over n in the next copy, an 8 over n in the next copy. There's an 8 over n in every single copy. So I can factor out that 8 over n, and what I have left is the sum from I equals 1 to n of the number 1. But then you're not done. Look at this term in each copy. It's a 16i over n squared. So in the first copy, it's 16 over n squared. In the next copy, it's 16 times 2 over n squared. In the next copy, it's 16 times 3 over n squared. So every single copy has a 16 over n squared in it. But what changes in the summation is I. So I can rewrite it like this. I can factor out the 16 over n squared that appears in every single copy, and then what's left behind is just the I. Similarly, every copy of this has an 8n cubed in it. So I can factor out 8 over n cubed, and I got the sum from I equals 1 to n of I squared. Hey, good news. The sum from I equals 1 to n of 1 says up here that's n. The sum from I equals 1 to n of I says up here that's this. This. We prove all those using induction, I guess. But I didn't ask you to prove these. I asked you to take my word for it. So let's see what we got. We got the limit as n approaches infinity of 8 over n times n plus 16 over n squared times n plus 1 over 2 plus 8 over n cubed times, I kind of want to FOIL this now, but I'm not going to. I'll do it later. N times n plus 1 times 2n plus 1 divided by 6. Whew. Okay. How am I doing on room here? Plenty of room. What do you want to cancel? I'm going to end up getting a common denominator. And my least common denominator is going to end up being n squared. So, okay, I'm going to do this in 2 steps. This might be inefficient. No, I'm going to be efficient. My least common denominator is going to be n squared. And I can tell that because the least common denominator here is 1. And here I can cancel out this n and this n squared and get a 2n down on the denominator. But the 2 I can cancel with the 16. So it'll leave me with just an n in the denominator. And here, I guess if I don't want to deal with decimals in the top, I shouldn't make the least common denominator n squared. I mean, I could cancel this n with one of the n's here, but I still have this 6. So let's cancel this 6 and this 8 to make it a 4 and a 3. And let's call our least common denominator 3n squared. I better do this in 2 steps. Okay, so what I have here is 8 plus 8 times n plus 1. So this 16 and this 2 made the 8. This n and one of these n's canceled, so that's divided by n. Plus, this 8 and this 6 cancel, at least somewhat, to make this a 4. This n and one of these n's cancel, so I got n plus 1 and 2n plus 1. And then I'm going to divide that by this 6 turned into a 3 when I canceled it with this 8, so I got 3n squared. Here. Evaluate this limit. I don't really want to, but I should. So you have a couple options in terms of how you do this. You can get a least common denominator for this whole thing, although there's other ways you can do it too. You can take the limit as n approaches infinity of 8, just say that that's 8, plus the limit as n approaches infinity of 8n plus 8. Okay, write this out. I could say, now I'm going to do this the way I showed you to do this in class. The limit as n approaches infinity of, and then I'm going to make this whole thing over one common denominator. You don't have to do it that way. You can take the limit as n approaches infinity term by term, and it'll work out fine. But I'm going to choose not to do that. I'm going to instead get a common denominator. My least common denominator would be 3n squared. So to get this 8 over 3n squared, I better make it 24n squared. And then here I have 8n plus 8, but it's only over n, and I want it to be over 3n squared. So I better make it 24n squared plus 24n if I want to make it over 3n squared. And then from this last one here, it's already over 3n squared. That's good news. So all I got to do is write the top. Although while I'm here, I'm going to FOIL things out. n plus 1 times 2n plus 1 is 2n squared plus 3n plus 1. And if you multiply that 4 through, you get 8n squared plus 12n plus 4. Because it was 2n squared plus 3n plus 1, and then we took the 4 and distributed through. So really what I have here is this is the limit as n approaches infinity of, let's combine like terms. For my squares, I got 24 plus 24 more plus 8 more. That's 48 plus 8 more is 56 n squared. What about my n's? Well, I got 24 here and 12 here, so I guess I got 36 of them. What about my constants? Just got 4, and that's over 3n squared. The limit as n approaches infinity. How about let's factor out an n squared from everything. Let's say this is the limit as n approaches infinity of 56 plus, no, let's do this differently. 56 over 3 plus 36 over 3n plus 4 over 3n squared. That's just splitting up with our denominator and then canceling where it was obvious, the n squareds, the n's, and leaving them. Well, I can evaluate this limit. The limit as n approaches infinity of 56 thirds is just 56 thirds. The limit as n approaches infinity of this guy, this would be 36 over a huge number, which gets really, really close to 0. Likewise, 4 over a huge number gets close to 0. What I get is that my answer is 56 thirds. You don't got to check your answer. But if you were so inclined, you could check it. You could say the integral, maybe note, the integral from, what am I doing, 2 to 4 of x squared dx is just is 1/3 x cubed evaluated from 2 to 4. This is using the evaluation theorem, aka the fundamental theorem of calculus part 2. And so all I got to do is take this thing, plug in a 4, take this thing, plug in a 2. So I got 1/3 times 4 cubed minus 1/3 times 2 cubed. So I have 1/3 times 4 cubed is 64. 2 cubed is 8. So what I get is 64 minus 8 is 56. Times 1/3 is 56 thirds. Looks like a nice little check there. Didn't have to do that, just an FYI. Okay, the last problem. By now your brain's probably pretty fried. Well, I got bad news is that I saved some of the hardest stuff for the end. Determine this using a u-substitution. Okay, so what you want to do for a u-substitution is pick something so that the derivative shows up here. And you're like, well, I don't know if I can make that work. Well, what you could do is that u equal x plus 1. I'm like, wait, but then wouldn't du just be equal to dx? Yes, it would. So then how does this work? I got that this guy would be equal to the integral from, and I'm going to write x equals 0 to x equals 1 here. I don't care a whole lot, but since I'm going to switch from x's to u's, I should switch my endpoints of integration from x's to u's. U's are always just one more than the x's. So I could say it's the integral from 1 to 2, or I could say it's the integral from x equals 0 to x equals 1. Maybe I'll even write that. Or the integral from 1 to 2 of something. And what is that something? Well, if u equals x plus 1, then x equals u minus 1. So up here where I have x minus 1 being squared, I really have u minus 1 being squared. So what I really have is u minus 2 up in the numerator being squared. Down in the denominator, I got u cubed, and instead of dx, I can write a du. Gets me here. Or you could have written it with the different limits of integration to make it look like this. Either one's totally fine. If you're leaving them with x's, leave them with x's. If you're changing them into u's, then, well, your u's are one more than your x's. At any rate, I'm going to stick with this one in blue here. This is something that eventually I'll be able to integrate, but I don't think I'm quite ready to do it yet. Maybe I can FOIL out the top to get u squared minus 4u plus 4 over u cubed. And why does that help? Because I can think about this as u squared over u, which is u to the negative 1 power, minus 4u over u cubed, which is negative 4u to the negative 2 power, plus 4u to the negative 3rd power du. And the nice thing about thinking about it like this is these are a bunch of terms that I can integrate. My first one will be u to the negative 1 power. My next one, I can pull out the negative 4 because that's just a constant. And figure out what the integral of u to the negative 2 is. And I can pull out my positive 4 and figure out the integral from x equals 0 to x equals 1 of u to the negative 3rd power. I guess each of these should have a du on them. You knew I'd forget that. Okay, so let's do the integration. U to the negative 1, the integral of that is the natural log of the absolute value of u, minus 4 times the integral of u to the negative 2. Well, using the power rule, if I added 1 to the exponent, I would have u to the negative 1 power. But then I'd have to bring the negative down in front, and that would make this a positive. And same idea here, my new exponent would be u to the negative 2 power, but if I were taking the derivative of this, I'd bring the negative 2 down in front. And so what must have been in front so that when I bring the negative 2 down in front, I end up with positive 2? Sounds like there was a negative 2 down in front. So I end up with something like this, and I want to evaluate this thing from x equals 0 to x equals 1. And I can do that, not yet, because these are still u's and I got to make them x's. So this is the natural log of, recall that u is equal to x plus 1, so the absolute value of x plus 1, plus, maybe it'll be prettier to look at this if I call it 4 over x plus 1, because raising something to the negative 1 power is the same as putting it down on the bottom of the denominator here. And similarly, I can make this, and I want to evaluate that from 0 to 1. I don't have to say x equals 0 and x equals 1 anymore because now my variables match up. Where are you going to do this? I don't know. Up here maybe? Plug in 1 everywhere, I get the natural log of 2. If I plug in 1 here, I get 4 over 2, which is 2. And if I plug in 1 here, 2 squared is 4, 2 over 4 is a half, so I get minus a half. And from that, I want to subtract. And now what I'm going to do is plug in 0 everywhere. So I get the natural log of 1. I get, if I plug in 0 here, I would get a 4, because 4 over 0 plus 1 is just 4. If I plug in a 0 here, I'd get minus 2. So what does this equal? Well, let's see. Let's simplify a little bit. I get the natural log of 2 plus 2 minus 1/2 minus 2. Where did this last minus 2 come from? Well, the natural log of 1 is just 0, and 4 minus 2 is 2, is positive 2, and I'm subtracting that positive 2. There you go. But wait a minute, positive 2 minus 2, isn't this just the natural log of 2 minus 1/2? Sure is. And that's the answer. Feeling good about yourself? Well, do it again. Figure out this same integral, but now use integration by parts. And hint, it's going to suck. You're going to have to do it twice. Okay, but I can do that. Well, wait a minute. With integration by parts, I'm looking for something times something else. This looks like something divided by something else. Well, how about we think about this as the integral from 0 to 1. And actually, I'm not even going to write this. I'm going to first figure out the integral from, or the integral of x minus 1 squared times x plus 1 to the negative third power dx. I'm not going to worry about the limits of integration. I'm going to calculate this thing first and then go back and answer this question. So let's see. I guess it would be a good idea to call u x minus 1 squared. How do I know that? Why do I want that to be u and dv to be x plus 1 to the negative third dx? It's because what I choose for u is the thing that will get simpler when I take the derivative. If you take the derivative of this, it gets worse. Take the derivative of this, it gets nicer in some sense. I'll show you. Let's take the derivative. The derivative of this guy would be 2 times x minus 1. If dv equals this, then v must be equal to the antiderivative of this. So I would have x plus 1 to the negative 2 power if I add 1 to the exponent. But wait a minute, if I brought this negative 2 down in front when I was taking derivatives, it would have given me a coefficient. I don't want a coefficient. I better put a negative 1/2 here, so the negative 2 will cancel with it. Here are my pieces. I can use my integration by parts formula. Maybe I should have written that somewhere. The integration by parts formula tells you that the integral of u dv equals uv minus the integral of v du. Okay, so the integral of u dv, the integral of this times this, is equal to u times v, x minus 1 squared, times negative 1/2 x plus 1 to the negative 2 power, u times v minus the integral of v, negative 1/2 x plus 1 to the negative 2. This is all v. I still need my du, which is 2x minus 1. This should have a dx on it. It's a little bit sloppy there. So this would have a dx right here. Okay, so what do you got here? Well, let's clean it up a little bit. First of all, this thing is negative. This is a negative exponent, so I can think about it as down on the bottom of the fraction. So here's the negative from this negative. I got x minus 1 squared up on the top of the fraction, and down on the bottom of the fraction I have this 2, and I got x plus 1 squared minus the integral of this thing, but this thing is negative because I have this negative right here. So this negative and this negative will cancel, and I'll get plus. And then I have this 1/2 constant, but I also have this 2 constant. So those guys will also cancel, and I'll be left with x plus 1 to the negative 2 power times x minus 1. And you might be able to figure this out using a different way, but I did say to use integration by parts twice. So I suppose we better repeat this process. We'll leave this part alone. And then I'll figure out this integral. Plus, well, maybe it's time to switch colors. Let's see, staring at this thing right here, the integral of this guy. Playing the role of u, I'd want to be this thing because this is the thing that gets simpler when I take its derivative. So u is x minus 1, and therefore du is dx. And dv, by process of elimination, would be x plus 1 to the negative 2 power, and therefore v would be equal to, well, I got x plus 1 to the negative 1 power, but I need to switch the sign so that when I bring the negative 1 down in front, I get the 1 as the coefficient here. So I get these parts. So let's put these in. Using my integration by parts formula, I know I have the integral of u dv equals u times v. So I got x minus 1 times the negative of x plus 1 to the negative 1 power. There's uv minus the integral of v, which is this mess. I'm going to be smart here. Minus the integral of a negative. Let's just call that plus x plus 1 to the negative 1 du, which is dx. So you get here, I can say this is this mess again. At this point, you might just say same as above or something. Plus, nope, not plus. This thing's negative, so let's just write a minus here. In the top, I got an x minus 1. On the bottom, I got x plus 1. This and this. And then to that, I want to add the integral of this guy. Well, the integral of x plus 1 to the negative 1 power is the natural log of the absolute value of x plus 1. And I guess there should be a plus c here. So this right here is the answer to this. Unfortunately, this is not what was asked. This is what was asked. All right, so it being green. So the integral of, from 0 to 1, of x minus 1 to the second power, aka squared, divided by x plus 1 cubed will be equal to this thing evaluated at 1 minus this thing evaluated at 0. So let's evaluate this thing at 1. If I evaluate it at 1, I get the negative of 1 minus 1 is just 0. That's nice. So I don't care what this is. This is all 0. Minus, evaluate a 1 here, 0 over 2, that's 0. Plus the natural log of 1 plus 1, I guess that's the natural log of 2. Plus c if you want. Minus this same thing, but now evaluate it at 0. Okay, evaluate this at 0. If I stick in a 0 here, I get negative 1 squared, which is positive 1. But I have this negative here, so I get negative 1. And then down in the bottom, I got 1 squared is 1 times 2. I think I get negative 1/2 out of this mess. And here, if you plug in a 0, you'll get negative 1 over 1. But you're subtracting negative 1, so you're actually adding 1. Plus the natural log of 1. Let's see what we got here. This is the natural log of 2 minus negative 1/2 plus 1 is positive 1/2. And the natural log of 1 is 0. So I get natural log of 2 minus 1/2, which I pray is what I have here. It is. How about that? That's my answer. Hope you have a good weekend. Sorry for ruining it with such an impossible quiz.